All right, today we're going to pull back the curtain on something you can't see, but is happening all around you, all the time. This wild, chaotic dance of molecules. This is the stuff that explains the very air we're breathing, and really, it all kicks off with one pretty simple question.
So let's start right there with that fundamental question. When you hear it's, say, 75 degrees Fahrenheit outside, what property of the air are we actually talking about? It seems like such a simple question, right? But the answer is going to take us deep into this hidden world that makes up absolutely everything around us. So let's figure this out.
You know, the famous physicist Richard Feynman once said that if all of scientific knowledge were to be destroyed in some catastrophe, and only one sentence could be passed on, this would be it. He called it the atomic hypothesis, and it's the absolute key to everything we're talking about. See, the answer isn't that air is empty. Not at all. It's that air is jam-packed with tiny, tiny particles that are in constant, violent motion.
So let's really dig into that idea, into this world of atoms. Because getting this isn't just some neat little piece of trivia. No, it's the bedrock, the foundation for understanding how all gases behave. And scientists have a name for this whole framework, the kinetic theory.
And here's the beautiful thing about the kinetic theory. It boils everything down to one super elegant idea. A gas, like the air in this room, isn't some smooth, continuous thing. Not at all. It's really just a massive collection of individual little particles all zipping around randomly at incredible speeds, just bouncing off of everything.
Okay, but trying to track trillions upon trillions of these particles all at once, that's just impossible, right? So to get a handle on all this chaos, scientists did something really clever. They created a simplified model. They kind of set up some rules of the game for an imaginary gas that behaves perfectly. And they called this model an ideal gas.
So what is this ideal gas? Well, you can think of it as our simplified, almost cartoony version of reality. We pretend the molecules are just these tiny little points so small they have basically no size. And we imagine they're always moving, and that when they hit each other, they bounce off perfectly without losing a single bit of energy.
So these are the basic rules for our model. Rule 1, the molecules are constantly moving, completely at random. Rule 2, they pretty much ignore each other until they collide. And Rule 3, every single collision is perfectly elastic. Think of them like microscopic, indestructible billiard balls that never ever lose speed when they hit something. And it's these simplifications that, believe it or not, let us predict what's going to happen in all that chaos.
Okay, so now that we have these rules, this is where it gets really, really cool. We can finally start to connect this invisible, microscopic world of bouncing molecules to the stuff we can actually see and feel in our everyday lives. Things like pressure and, maybe most importantly, temperature.
So to really see how this works, let's just zoom in on one single molecule inside a box. Picture it. It's flying straight towards one of the walls. It hits the wall, bam, and bounces right off. And because we're saying these collisions are perfectly elastic, it bounces back with the exact same speed it had before, just going the other way.
Okay, so that one little bounce gives the wall a tiny, tiny push, a little transfer of momentum. Now take that one tiny push and multiply it by trillions of molecules hitting that wall and every other wall every single second. What do you get? You get a constant, steady, combined force, and that force is what we feel as pressure.
All right, so pressure is basically a constant bombardment from these tiny molecules. Got it. But that just leads to an even bigger question, doesn't it? When we say something is hot or cold, what are we actually talking about? What's really going on at the molecular level? What is temperature?
And here it is. The answer is so elegant and simple. Temperature is just a measurement of the average kinetic energy of those molecules. To put it even more simply, hot just means the molecules are moving fast, cold just means they're moving slow. That's it. When you heat something up, you are literally just making its molecules jiggle and zip around faster.
So just how fast are we talking here? Well, a typical nitrogen molecule in the air around you right now is moving at about 516 meters per second. That's over 1,100 miles an hour. That is literally faster than the speed of sound. And what's even crazier is that's just the average speed. In reality, you've got this whole distribution of speeds. Some are going slower, some are going way, way faster, all mixed together.
Okay, so if temperature is all about the energy of motion, that brings up another question. Can molecules move in different ways? Besides just flying through space. And if they can, how is all that energy shared? Well, this leads us to this really cool idea called the law of equipartition. It's all about how energy gets divvied up among all the different ways a molecule can move, or what physicists call its degrees of freedom.
And this law is just beautifully simple. It basically says that when a gas is just sitting there, not really doing anything special, what we call being in equilibrium, the total energy in that gas gets shared out equally among all the possible ways a molecule can move or store energy. It's like fair shares for every possible type of motion.
So let's make this concrete. Take a single atom, like helium. It's just a little ball. It can only move in 3 ways, right? Up and down, left and right, forward and back. That's 3 degrees of freedom. But now think about a molecule made of 2 atoms like the oxygen we breathe. It can do all that, plus it can tumble end over end, kind of like a little Dumbo. And it can do that in 2 different ways. So that gives it a grand total of 5 ways to hold on to motion energy.
And here you can see exactly what those 2 extra motions are. This 2-atom molecule can spin around a vertical axis, and it can spin around a horizontal axis. You can think of these rotations as extra buckets for the molecule to store energy in, on top of the energy it has just from flying through space.
Now, this isn't just some abstract idea. It has real, measurable effects. Because those 2 atom gases have more of these energy buckets, it actually takes more energy to raise their temperature by 1 degree. And using this logic, the kinetic theory can predict a number called specific heat for different types of gases. And the amazing part? When we go into the lab and measure it, the predictions are spot on. The theory actually works.
Okay, so we've built up this really powerful picture of what a gas is. But there's one last little puzzle piece, something that might seem to completely contradict everything we just established. It's a final, really interesting question about how these ridiculously fast molecules actually travel from point A to point B.
I mean, think about it. We just said that the molecules in the air are flying around faster than a speeding bullet. So if your friend opens a pizza box on the other side of the room, shouldn't you smell that deliciousness like instantly? Why does it take a few seconds for the smell to get to you? What's going on?
Well, the solution to this little mystery is a concept called the mean free path. And it's simple. Even though a single molecule is moving at an insane speed, it doesn't get to travel very far in a straight line before it smashes into another molecule and gets sent flying off in a totally different direction.
So the journey of that pizza smell molecule across the room isn't a straight shot at all. It's more like a chaotic, drunken stumble. It moves a tiny distance, collides, changes direction, moves another tiny distance, collides again. It's like a microscopic pinball bouncing around billions of times. And that is why it takes so long for smells to travel, or what scientists call diffusion.
And this right here is the ultimate takeaway. The kinetic theory is this powerful bridge. It connects the microscopic behavior of atoms, these tiny particles zipping and colliding, to the macroscopic properties we can actually measure and feel, like pressure and temperature. It makes the invisible visible, and it gives us a whole new lens to see the world through.
And what's amazing is just how successful this simple model has been. It doesn't just explain pressure and temperature. It's the foundation for the famous gas laws. It explains things like how smells diffuse across a room. And it even lets scientists make the first good estimates of the actual size and mass of molecules. It's truly one of the cornerstones of modern physics.
So we'll end on this thought. The next time you feel the warmth of the sun on your skin or the biting chill of a winter wind, just remember what you're actually sensing. The frantic and visible dance of countless atoms. And it leads to a final question. In a universe built on perpetual motion, a universe where everything is constantly jiggling and moving, is anything, anywhere, ever truly standing still? It's a thought that reminds us of the incredible, dynamic world hiding just beneath the surface of everything we see.